Good morning, folks, and I want to thank you all for taking time out of your busy schedules to join us here at ARC in Orlando for hopefully what you thought was a informative and somewhat interesting session, and hopefully this session you'll find is equally informative and interesting as well. My name is Tim Shea. I'm a senior analyst at ARC. I've been there about a little over 9 years, and primarily I've been focused on the upstream, midstream oil and gas technologies and solutions. Do some work on aftermarket retrofit, compressor and turbine monitoring and controls, optimization, I guess, if you will, and I've been focusing a lot on obviously oil and gas and analytics. So we've got 3 tremendous speakers today, so I'm going to be kind of relatively brief. I've got a few Slido questions, I guess, if I could figure out how to do these. But the housekeeping, they ask if you can ideally try to turn your phone on vibrate, provide feedback through the ARC Forum app. Obviously it's the last day, so there's not much in terms of hopefully everybody had some fun, had a chance to look at the penguins and the whales or whatever they had last night, and maybe get on that roller coaster ride. You wouldn't catch me on that because wouldn't be a good situation. And just ask questions. We're going to have a Q&A after all the speakers are done, and we're going to have a great panel discussion. So so now I'm going to launch my Slido surveys here. We'll see how well it works. So basically, I don't know what happened there, but you're logged out. Okay. There's supposed to be like a QR code. Is that there? Oh, maybe not. Bear with us as we have a. Well, there's supposed to be a QR code. If you have a couple of seconds, you take a picture of it on your phone. A little link will come up, and then you can. They're pretty quick questions, yes or no, and some maybe multiple choice questions. So anyways, how's everybody like the weather? Huh? Pretty good? How about them Celtics, huh? There you go. Now we're talking, right? Hopefully there's no one here that's a Golden State fan, but there we go. Oh, that's the first question. So if you want to take that, do a quick QR code. We're just trying to get a sense as to how many guys. I'm hoping a lot of people here, they're oil and gas or chemicals or whatever industry you're. In my personal opinion, if you haven't started this journey yet, then you're personally and professionally negligent. But that's my own, not an ARC opinion, of course. That's my own opinion. But because there's so much going on with the digitalization of your operations, and obviously if you're in oil and gas and you've survived the volatility over starting in June of 2014 and up until now, there's been a little bit of volatility, which I guess is common for the oil and gas industry, and obviously chemicals and some other ones. So it's encouraging that the number's pretty high. I wouldn't expect it to be quite 100%, but I hope it's going to be pretty high. So we'll give you guys a few seconds to take time to do those surveys, and so it looks like about 85, 15. Okay, that's good. And maybe, I don't know, can I come back to these later on and see if they've updated later on, or? Oh, you don't know? All right. Okay. So then the next one is, obviously, if you answered yes, for which operational areas or applications have they been deployed? So we got seismic reservoir management. Obviously, there's a lot of big data going on there. Before big data was big data. Drilling and completions. I mean, there might be some intelligent completions going on, or drilling optimization, artificial lift and production. That's obviously optimizing ESPs, PCPs, rod pumps. And then there's pipeline integrity management, which is kind of encompassing. That could include, pipeline integrity with corrosion monitoring, and the integrity of the pipe. It could be leak detection. So there's a pretty broad. And then there's other, which is obviously probably where most people are answering, and then refining and downstream is, I'm pretty sure that there's some use of analytics for quite a while there. They're probably about 10 or 20 years, depending on who you talk to, ahead of the upstream. So, but it's interesting that, I find it interesting that, well, I guess I'm curious what a lot of those others are, because, I mean, I tried to be I couldn't add up, 20 options, but I mean, there must be a lot of, it must be predictive maintenance. I guess you could have a lot in there for predictive maintenance, rotating equipment and things like that, or any number of things. And chemicals. Yeah. Well, someone told me you should only limit it to so many. And then, of course, one of my colleagues, I took one of his surveys, and he had like 15 or 20 items and ranked them. And I'm like, well, how the hell did he get that? Someone told me that, I would have added more in here. But anyways, I don't know if they'd even fit on the screen. But anyway, so you get an idea that there's a lot of areas for opportunity to obviously optimize production. Obviously, most people and many industries, particularly in oil and gas, are really trying to lower the cost per barrel of oil equivalent. It's a big factor, increasing production. So that's good. That's right. And then I think we have one more. If you're one of those 10 or 15% of the people that's not doing this, if not, then when are you planning on doing it? You got something going on right now? Are you looking at it next year? I mean, we're just curious as to, I hope that's a pretty short time period, because my personal opinion is that if you're not doing it by now, then man, you really are behind the eight ball. But I'm sure there's some guys, particularly private companies that are maybe smaller and independent that might tell me to go fly a kite, but that's another story. But that's all right. So that's good. So it looks like if you're not doing it, you're probably going to you're thinking about it pretty quickly. So that's an encouraging sign. I guess did it go? Does it go to the next slide, or I guess not? I don't know. But there's supposed to be another slide after that, but we'll. Oh, there we go. Oh, there we go. We'll go back to the. Is there no more slides? What happened to all my other slides that were there? Okay, I guess I'm going to be a little shorter than Anyways, there should be some slides there, but we'll figure that out later on. But basically, in my slides, I was going to talk about a number of different things, list a bunch of applications where we're seeing people are using them for, intelligent completions, pump optimization, you name it. There's a number of applications, and there's a lot of areas operationally where oil and gas and chemicals and, pulp and paper, and a lot of these guys can really benefit from utilizing, because it's really software. What I found was interesting is that when I watched the Bank of America keynote, then I saw how much money was being spent on software and in manufacturing, and how little was spent on oil and gas. It was less than I thought. I knew it was going to be a low number, but I didn't think it was going to be that low. So it really tells me that you oil and gas guys and others have got to get your you got to get your heads in gear and start getting a little bit more, looking at the stuff a little more seriously, because I think there's a lot of value. Based on the research we're seeing, the people we're talking to, there's a lot of activity in using, analytics and industrial Internet of Things and to optimize operations. And then I had, talking about the business case. And the one thing I want to give you the takeaway is that I always tell people that technology is only at best half the equation. And we've had a number of clients, pay us to audit their plants or talk to their folks in different parts of their operation to see, are they ready for this digital transformation? I mean, are they ready culturally? Are they ready with their work processes? Because that's where I think you can. And I use this example of a guy I talked to about. He had one of these OEMs that had he had a really nice looking pump optimization solution. You put it on there, it does all the vibration monitoring and all this other stuff. And he said, the technicians would take it off in the field and run it over with a pickup truck. So you've got to get the people to, kind of embrace this new stuff. And you got to educate them and be transparent and say, look, we're not trying to take your job. We're trying to empower and augment what you do. And, if I was one of these guys, I would probably take advantage of any opportunity to train, to learn new skills, because this is what's going to happen. I'm sorry, go ahead. Oh, it's ready. Okay, all right, so. That's okay. So anyways, this is kind of what we're talking about. Companies are obviously, you've heard a lot about people talking about the cloud and the edge, and I think that's so people are really, acting accordingly in that area. These are just some of the list, and you'll get a copy of this later on. So different applications and things that we're seeing. I think a big area could be like, pipeline monitoring, pipeline integrity, and not just leak detection, but also, integrity, asset management of the pipelines, compressor and pump stations, things like that. And obviously methane and leak detection is going to be, because obviously ESG is increasingly, particularly if you're a public company, it's increasingly becoming a pressure point for companies is to not only track and monitor, but mitigate, methane and leak detection for obvious environmental, and obviously it's just good business practice in my opinion. And this is kind of a slide that I took from one of my colleagues that, he's kind of he's one of our digital twin guys, and if you come to me with a question, I'll direct you to someone else in terms of it looks nice, and it's basically it's talking about how, everybody talks about what is a digital twin, and everybody can say, I get a digital twin, and and he can say, well, anything with simulation could be theoretically a digital twin, but we try to put some parameters around it in terms of obviously these process modeling with engineering simulation. There's a lot of activity going on 3D and particularly in like dashboards and things like that, because you can have a lot of data, but you need to have that data visualized to somebody at the right time, the right person, in the right amount, because you don't want to, obviously looking at alarm management, alarm overload, data overload could be a huge problem. So trying to manage that whole process is going to be critical. And then obviously, data is kind of like the new oil, the new gold. I mean, getting your data, making sure its data is hygienic and clean, and managing, like people talk about, digital twins, but one of the biggest things in digital twins is how do you maintain and sustain that digital twin? Because you need good data, you need, so data governance and things like that. So there's a lot of issues in that area that you may have already heard during this conference. Challenges, obviously, in the oil and gas, it's anywhere. It's really containing costs, increasing productivity, and increasing collaboration. And someone mentioned it in a session in the last day or two. I always talk about in oil and gas, you've got internal ecosystems and external ecosystems. You'll have multiple partners on a project, then you'll have multiple contractors, drilling guys and oil field service guys. You'll have a number of people. And you're trying to, I used to call it, I hate to say it, but I used to say it was a dysfunctional orchestra, and you need to try to get everybody to stop playing on the same tune and getting that fine tuning that, and we're seeing a lot of that, because everybody, you've heard by now that there's no one that's got the silver bullet. No one's got this all figured out, and no one company's going to be able to do all this. So you really need to build a strong ecosystem of partners. And then, you can talk about the great crew change. I mean, obviously, a lot of people with the recent layoffs, due to the pandemic, I think some people that I knew that were in the industry for quite a while, they just said, hey, I've had enough of this, and they're moving on to other things. And that's going to be a challenge for companies, to try to compete against Google and Facebook and Meta, and AWS and all these other guys that they have, because kids want to do the cutting edge stuff. And I think oil and gas with this new technology is a good way to help recruit people, in my opinion. Challenges, obviously, if you were here on Monday or Tuesday, there was a great guy from Clint Walker from the Department of Homeland, from the Department of Homeland Security, great presentation. Cybersecurity is like, it's like beyond table stakes. It's like your DNA. You got to have it. Obviously, standardization, obviously like subsea, if you're talking about subsea, just the documentation alone is, the customization there and all that stuff. So they're trying to really move towards standardization, modularization as much as possible. Again, it's to cut costs and to, speed time to the oil, or whatever, the speed time to market, or whatever the case may be. And there's obviously increasing societal and political and increasingly investor, if you're a public company, you're increasingly getting a lot of pressure from BlackRock and others to, really what are you doing sustainability-wise? So I think that's going to be, and obviously I'm sure people have talked about it, but using digital technologies to help you not only lower costs and increase production, but it's going to help you meet your sustainability goals. I mean, you got to measure this stuff, you got to monitor it, and you need to report it. So that having that kind of data is going to become increasingly critical. And then obviously the complexity of what's going on, integration. We looked at some projects, in different areas. And the key challenge that a lot of users and operators talked about was the integration of all this stuff, trying to make all this stuff work, break down those silos. And again, that goes back to people, culture, and processes. Yeah, we talked about this, cost reductions, streamlining operations, particularly if there's a lot of, people are selling off assets to other people, and, you're picking up assets. So a lot of that, and then just trying to manage all that, getting all these different, architectures and systems to work together, and, all that stuff is increasingly complex. With the pandemic, obviously, they increased the need for remote operations, and I think there's a big push right now. You're going to hear a little bit about connected workers in the next speaker here. Obviously, optimizing production, again, while ensuring, how do you manage that big, I used to always tell people that, hydrocarbons, that segment is like a big glacier. It's melting slowly. Some people want it to melt faster, and some people realize it's not going to melt as fast as they think. But how do you manage that migration, to these other alternative energy sources? And then again, sustainability. There's some people would accuse some companies of greenwashing, and then there's others that are really, taking. But everybody is basically saying we got to do this. Everybody's kind of migrating and managing it to their own pace. And then it basically, I kind of talked about the need for an ecosystem and particularly strong technology partners, companies like Wood and Microsoft and others that are, going to be able to help you navigate this journey. Because, like I said, no one's got it all figured out. And a lot of these guys in like an oil and gas or chemicals, I mean, that's what they focus on. I always tell people like, stick to your knitting and pick best of breed partners to work with, because then you're going to save yourself a lot of time and pain and probably, hopefully, money. So there's a kind of a busy slide, but you can probably pick it up, reducing NPT, things like that. So that's it.
Okay, good morning. Thank you everyone for being here. It's a pleasure for me to present a collaboration between Halliburton and Honeywell to digitize inspection workflows in the upstream for oil and gas. My name is Raid Sharrouf. I'm the head of production and reservoir management in Halliburton Landmark. I've been in the industry for 20 years, initially in the automation space, and then I moved to production and reservoir management. And during this journey, I've been deploying digital oil field solutions for different customers. And the first question that they ask is about, I want to do a digital oil field. I want to connect. I want to optimize production. But the two challenges that we have faced is that our first, the data integration, I mean the disconnect between the field and the engineering side. So we have engineers doing production optimization. We have engineers using models, but the data is not there. And the second challenge that they have faced is that the human factor. So the human factor for operations is a second challenge. So all those connectivity or all those activities that are done in the field are not aligned with the engineering side of the house. Now, in downstream side of the house, it's common to have a lot of automation, a lot of sensors, reading systems, etc. But when we go to upstream, especially in the land, it's a different story. So just to give you an example of how upstream looks like. So we have wells, normally with very minimum instrumentation or not instrumentation at all, with very minimum connectivity to the field, from the field to the headquarters. And we have people that have to go manually, take the data, bring it back to the headquarters, do the activities, and do the activities in a scheduled manner. So they have to go once a week, twice a week, in different time schedules. So that brings a lot of inefficiencies to optimizing. That is the first challenge, to optimize the production. You are not able to optimize if you are not able to measure, if you are not able to manage your crew and your human factor in that sense. So what are the unique set of challenges that we face in upstream, especially in land operations? First, we have large amount of data and across diverse geographies. So wells, as difference from downstream, you have a facility, and inside that facility is located in one area. You have, in upstream, you have wells, and those wells are scattered across a big area. There is disconnection between assets and the headquarters and the operations. There is manual paperwork, so when that data comes, the operator has to fill it into the systems. Then when that data comes into the engineer to perform an analysis, to perform a diagnosis, then that data, it's too late to perform an optimization. Of course, there are rapid change in the market regulation, and therefore in the crew, there's a layoff happening in the oil and gas industry. Then you ramp up the crew. There is a new crew being hired. So how to capture that knowledge and that processes, and to standardize that way of work. And of course, there is a high pressure on the carbon intensity activity. Why? Because if you have to drive, on a schedule to go and do some activities just to gather data from the well, right? If that well is running okay, then you have, a higher carbon intensity on those runs that you are doing. So it's estimated that there is a big loss on opportunities on efficiency that can be gained just automating those inspection routes. So what does an asset operation or digital asset operation looks like? So first is be able to automate or to digitize those daily activities, be able to track the crew performance and the availability of the crew, so sending expertise on demand to the different activities. Of course, track the HSE indicators. Be able to not just digitize the activities for the crew, but also to provide to the crew the best practices and the standard procedures, so they have in their hands the different procedures. Be able to manage a scheduled routine like chemical injection, preventive maintenance, well test, oil hauling, etc. But be able to do that not just on a schedule, but do it on demand. Now, how we architected this solution? We partner with Honeywell, and then Honeywell, it's leading on the connectivity side of the house. We, in Halliburton, manage reservoir management, well modeling, well engineering. We create the connectivity to the wells and transmission of those variables. The second, it's integrate that data, that it's time series data or maintenance data, with the data that we do have in the headquarters, like the well test, the reports, the downtimes, etc. We connect that with the physical models, which reservoir models and well models, and we create what Tim was mentioning, which is the digital representation of the asset, in this case of the well. Now, that will generate the set of recommendations of activities that need to be passed back into the operations in those scheduled rounds. Now, how that piece of passing back the activities to the field it's done? Well, basically, after those recommendations are done, you have the concept of the assets, you have the list of activities that need to be done, that it's passed into the platform, into Honeywell platform. It's run on a schedule or on demand. It's passed into the device of the operator, so you get the list of activities, you control what is the step-by-step that you have to do in your inspection round. You actually control, you can control that or avoid that one activity cannot be done before the other. You can put prerequisites for the activities. And one important thing of this solution is that because most of the wells are in places where you don't have coverage or you don't have signal, you need to be able to work offline. So you work offline, you collect that data, and once you are back into a coverage area, you synchronize back and get into the platform. But here is where the interesting thing comes, because that data, it's normally in operations is used for equipment reliability, or is used for operations, be able to have the well in uptime. Now, having that data connected in the operational platform with the engineering platform, you can build more advanced workflows like well integrity management, production accounting, production allocation, production optimization. Now, the solution that I have presented, it's just one of the pieces of what we have teamed up to do with Honeywell. Actually, we are doing a complete connection of the surface and subsurface integration for connected asset. What that mean? That means acquire the data, which is basically the real-time piece of of that, then connected to the modeling, and here is either data-driven models or first principle reservoir modeling, to be able to connect reservoir wells and facilities. So in that case, we can do the entire value chain optimization. So we have from the pour to the sales point. So the benefits or of this implementation of the digital opportunities are first targeting challenges like the oil price volatility. It's actually targeting to address the investor pressure on capital expenditures and lowering emissions, as well as we have seen increase in those type of projects, increase in production, 4 to 10%, also 4 times increase in the workforce productivity in this type of solutions. And that's it.
So, hello, my name is Nicole Monk. I'm with Credence Energy Services. Most of you probably have not heard of us. We're an oil field services company based out of Williston, North Dakota. I live 15 minutes from Montana, an hour from Canada, so I am very, very far from home and very, very humid weather compared to where I am from. So specifically, I'm speaking on behalf of OLI, which is the very first automation that we were able to integrate into our company. We specifically work in, as you said, a very remote area. Automation is very difficult for us for the fact that connectivity is very inconsistent. We've had times where I've been areas where I haven't had signal for anywhere from 30 minutes to 3 hours on my drive. For the most part, AT&T and Verizon apparently do not care about us, and we accept that as a challenge. So, I said, we are an oilfield services company. There are close to a dozen different service companies that work for any operator just to help give production wells a longer life. So our specialty is production chemicals. A little known fact about the Bakken where I work is the water that we produce with our oil is 30% total dissolved solids. It is more salty than the sea. It is a very fun time to work at. I'm just kidding, it is atrocious. I always say I'll retire in Texas where it is a lot easier to work. So, because of that, there's a lot of science that goes into what we do, and specifically one of our main things is we do complete water analyses to determine the amount of scale that's going to form and eventually would solidify a well over time. Most wells, you could get like a year, but we do have some wells that the actual well will produce solids to the point that will solidify and shut off the well over the course of 30 days. Again, it is a very difficult area to work, which is why we exist. So, a little bit of overview by numbers. My company services 2,200 wells in the Bakken. Over the 5 years that our lab has existed, we've completed 18,000 complete water analyses, 5,600 of which were just last year. Now, OLI Studio 11 was one of the amazing softwares that we consistently used, but there was one minor downfall. I happen to be the fastest one for modeling in my company, as I've been with the software the longest, and it takes me 3 minutes per model. Now with the 5,600 that we did just last year, that equals 280 hours or 7 weeks that I need to be sitting behind a computer. Now, most people would say, 7 weeks, it's not a big deal. But out of the 110 employees that I support, there are 4 people on my technical team that support all of our assets. That means that the opportunity cost of somebody sitting behind a desk is astronomical, especially when talent in North Dakota is so slim. Now, for people such as our regular engineers, it's a little bit closer to 5 minutes. I will admit they're slightly slower than I am, and that would equal to 12 weeks in a year. Again, opportunity cost for an engineer sitting behind a desk, it's just unprecedented to the point that we just quit doing the complete water analyses and doing the scale modeling that we needed to be able to keep our assets moving. It pretty much was a choice of, do you turn a wrench in the field or do you sit behind a computer? And the answer is, we're almost always in the field. So, the problem. Our company, we double in size close to every year, which is nice, but originally when we started working with OLI, we were in a singular location. Every single engineer was located in Williston, North Dakota, so we had a single user license. Then we expanded. We now have teams in Minot and Dickinson, the 2 closest cities, which are 2 hours and 3 hours away. I said, there's not a lot of people that live out there, and I understand why Verizon is not very active. So With having a single user license, that meant that anybody in the remote locations was required to request of the technical team or a local engineer to do the modeling for them. Now that meant, oh, you need something? Let me drop everything that I'm doing and get over to it. The answer was it never got done in the time frame they were looking for. And anybody that's working upstream will understand that the answer is, if I need it, it needed to be done yesterday. We're a very reactive and responsive area, so the time frame that we are working in is always very tight. Another thing is, most of you probably remember COVID. It was fun, happened in North Dakota too. So all of our people went to working from home. With a single user license, that meant that one person had to take on all of the modeling. That happened to be myself, which worked out all right. But when we came back to the office, I said, all right, engineers, you did it before, you can do it now. And they said, we don't remember. It's been a year and a half. I haven't used it. Held training classes, tried to get them back on, but they got so used to it not being a part of their daily routine that trying to squeeze it back into their schedule was impossible. And so it was, okay, well, do we attempt to reforce the issue and attempt to reintegrate that into their daily work-life schedule? Do we add more people to my team? What's the options? And luckily, the answer was the OLI Cloud API integration. Right at the time that we were coming back, OLI said, we can automate what you do. And I said, if you tell me I get more hours back in my day, I am here and I am ready for what you are offering. So between myself and our data systems manager, we came up with specifically a few key points. Automation, I said, is very limited for us. And so moving towards that point, we are very, very big skeptics. So the biggest thing was they had to meet a few key goals. We need to be able to pull in data in the already existing format. We'd spent thousands of dollars making our lab database. We were not going to be making any changes from there for the fact that it would just add more cost. We also wanted to make sure that this new automated system worked as well as the manual one that I was working with. If the data wasn't reproducible and wasn't as exact as the previous, we also didn't want it. Also, I said, we need a minimal human intervention. We are doing more with less as we keep expanding, which meant that we didn't have time for somebody to be sitting, and even if it only saved 50% time, it still probably wasn't worth it. We needed to have it that all of these scale models, for the most part, would just show up magically, which is what they now do, and also be able to use the output in our current data interpretation. Our company is minorly obsessed with Microsoft, so we just switched to Power BI. We were 100% Excel-based, if any of you can imagine what that world is like. So if it didn't work, we just were not there for it. So our final system was this data flow. So we have our lab database, which hosts 26 data points for every complete water analyses. From there, Jupyter is able to actually pull out the specified data, push it up into the OLI Cloud API. From there, all of the scaling risks were generated, pushed back into Azure for storage, and then shown in Power BI. The total answer from that was a complete removal of manual scale modeling. Now, this is something that for the most part had never been done before. Every single software that most people use in the backend is complete manual intervention. There's always a scientist sitting behind a desk, typing in all of the values, and then pushing that out. Moving to this meant that when my engineers go to Houston, or they're at home sleeping in Montana, most of my people do not live very close to our office, it made it that there was no geographic restrictions. There was no midnight phone call saying, this customer needs this now. Instead, all they had to do was open the internet browser, because we were able to finally automate something that everyone had always seen as, well, this is the way it's been done. You have to manually type things in, and then you get an answer out. This massively freed up our engineering and technical resources, which, as I said, I have a total team of 110. There are only a dozen engineers, and there are only 4 of us on the technical side. So the computer skills of the company are medium, and the background in chemistry, there are only 2 of us. Another big thing that this brought up was the ability for massive projects. So our production chemicals division has existed for 5 years, which means I have 5 years worth of complete water analyses on these production assets. Now, what a lot of people don't always recognize is the production wells that we work on they're living. They change over time. My end user and my customers, it's not actually people that pay me. It's not the BPs. It's not the Oasis. Instead, it's the earth. This is a living organism that changes over time, and we've been working to try to figure out, not only based on geographic, what scales we're working with, but how that might potentially change as the well produces over time, for the fact that it will go from 1,000 barrels of water per day all the way down to 10, close to 30 years later. With this, we were able to look at large-scale data and be able to output hundreds of complete water analyses and do geographical location searching to figure out if there was scale risks that changed over time. Overall, the automation opened up doors we never expected to be able to do large data looks to see specifically answers that we never looked at before of, do you want to drill in this location? Are you sure that it's the best choice? Maybe you should drill over here. You might have decent oil production, but you won't have to use nearly the amount of chemical to keep your well running due to the scaling factors. A big thing for us is 50% of the scales that we're forming in North Dakota are radioactive, which means the moment that it forms, it's radioactive material. I will tell you right now that it's very expensive to get rid of. So overall, this was the very first piece of automation we were able to bring in. For us, automation is a very limiting factor. So even just automating small pieces of software to save a couple hours, which in the end, looking from a value perspective is only $15,000, but from an opportunity cost when we have such little talent, ended up opening up huge doors. I mean, as a current right now, when I flew in here, out of our 4 team members, 2 were in Midland, Texas on business development, and I was here, which meant 75% of our assets were other places, which meant anything that we can do to automate, even the little things, ends up saving us so much time and lets us bring in new ideas to customers on the potentials for changes and the potentials for where you would want to develop. Well, that is all that I have, and I'll look forward to your questions.
Hello, everyone. My name is Manish Naik. I work as a technology principal in BP in a team that's called Digital Innovation. Our team deliberately looks at technology-first innovation. So we look at the horizon of emerging digital technologies and pick specific areas that no one in BP is looking at, and based on our understanding and experience of the oil and gas industry, we think those technologies are going to make a difference. So we start from there deliberately, and today I'm going to talk to you about an example which we have worked with Bonsai. Varsha is here from Bonsai, and Wood. Prabhu is here from Wood. They would join us later on the panel. And the specific use case is in the area of well completions. This area sits in historically what was known as Upstream. Now we call it production and operations. And the specific area where we have deployed this is in Gulf of Mexico. So I'm not a completions engineer, but I ran this past our subject matter expert, who is a completions engineer, who is effectively one of the 6 people in BP who does this for a living. And in his own words, eventually this use case will allow him to work on some other cooler areas in low carbon, such as carbon capture storage and geothermal, where his skills could be applied. So this is effectively looking at potentially automating the entire process end to end. But we start with, let's first start with understanding what well completions is and what part of well completions this use case sits in. So once you have drilled a well, before the production begins, you have to complete it. And the process of completing it is known as frac packing, which effectively, there's a substance, let's call it mud, which you have to drop through the annulus, and effectively you create a pack at the base of the well. And the quality of the pack is really important for various reasons, because you want to pack it well, you want to pack it quickly, and you want to pack it effectively such that the hydrocarbon that is producing out of it is coming out at an optimum rate, and there's no wastage from a safety standpoint, environment standpoint as well. And this is where the well completions engineers this is a big industry, and they have been, these guys are skilled, and the specific individual, Karthik, has been doing this for 30 years, and he uses his intuition in a frac packing job, which is effectively could be between 12 hours to 72 hours of really stressful work, where the individual is looking at a simulator and is trying to change the input parameters. The input parameters are pressure, temperature, solvency, and various other variables to look at effectively a pressure curve. And the pressure curve is what they then base their judgment on to understand whether the frac pack is complete and optimum or not. So our task at hand here was to see whether or not we could do this using AI and a specific kind of AI, and I'll come on to that in the next slide, and eventually see whether or not, so first test whether or not the AI could perform the same task at the human level, and then see whether or not, from our benchmarks in the past, whether the AI can beat the human performance as well in terms of optimization. There's loads of value if you can improve on the optimization side. I think I've been listening to this various talks at this conference, and I think most of the folks here understand the value of increasing sort of 0.1% of an optimization result as well. So there's tons of value both on the rig time in terms of the amount of time we would save during operations, as well as dollar value on increased production. So the size of the prize is big if we can crack this. And that's sort of the overall goal. And I'll talk a little bit about how we went about doing this, but I'll first start with the technology. So I think most of you would have heard buzzwords like AI and machine learning, and specifically machine learning at a high level. All kinds of algorithms sits in three different areas, and I'll give examples to explain this. The first area is supervised learning. This is effectively you train the machine by feeding it data, and over a period of time, the machine learns. So feed the machine pictures of cats, 100,000 pictures of cats, and gets to recognize cats and differentiate it with foxes, etc. That's supervised learning. And that same concept applies to various different types of data, textual data, tabular data, time series data, but it's the same thing. You feed the data, machine learns, and that's supervised learning. Examples like equipment health monitoring. I've seen few talks about things like equipment health monitoring. That's basically supervised machine learning. 95% of the work that you hear in machine learning is in supervised learning. Unsupervised learning is where you don't label the data when you feed it to the machine. So you just basically throw data at machine and the machine identifies patterns. Continuing with the image analogy, let's say you feed the machine with pictures of fruit basket with different fruits in it, and you feed like 10,000 images of those, and over a period of time, the AI would start clustering different fruits, saying, okay, these type of fruits are here, these types look similar, these types look similar, and then you can say, then you can label it. That's an apple, that's a banana. So that sort of clustering is a big use case of unsupervised learning. And very little happens in that space as well. It's still in research in terms of what you can actually deliver. And the third area is reinforcement learning, which is what we used for this use case. Now, I've often struggled explaining reinforcement learning to people who probably haven't heard about it before. So I think it's best to explain with an example. Imagine you want to design a robot that has to move from point A to point B by avoiding obstacles in the room. That's your task. Where you would start with is you would effectively create a simulator of the same environment, like a video game of the room, and represent all the obstacles in the room as well. And then the software agent, you let the agent go, and the agent takes one step, looks around, not hit an obstacle, I'm good. Another step, not hit an obstacle, I'm good. Another step, obstacle, start again. So it goes from being absolutely rubbish at start of doing what it's doing to eventually, over iterations inside the simulated environment, becoming superhuman and going from A to B. Never fails. And it compares the state against this notion of a reward, and that's effectively where I'll come on to when we talk about solution design. So that's the notion of learning in simulation iteratively and starting from scratch and eventually sort of learning, course correcting on the basis of a reward. So that's reinforcement learning, and that's the technology we chose for this project. In terms of selecting who to work with, so this is an area which at the time when we started doing this, this was getting a lot of press, and you would have seen videos of the Atari game where the machine finds a way to like immediately in one go beat the computer. or even things like AlphaGo, where the software agent has beat the world's #1 Go player 4-1. It was a big deal in Asia. It was like all over the news. And so those things were all reinforcement learning related. Gaming is where it had had its biggest success. And if you wanted to do something with this technology in the industry, you had to effectively work with open source code. You had to find talented people. You had to go to probably universities where there's research happening in this area. And why would they want to work with us when there's so many other cool applications? So that's where I think we spotted a company called Bonsai, which later got acquired by Microsoft. And Bonsai was in the business of, and Varsha can tell this to you better than me, but Bonsai was, I think still is, in the business of bringing the success of reinforcement learning from gaming into industry. And specifically, these kinds of industries that we are representing here is where there is a sweet spot for a few reasons, and I'll come on to that in a minute. So, I described the iterative nature of the process before, and effectively what we had to do was we had to represent that logic in the frac packing process. One of the big reasons why this project was successful was because if you think about how the completions engineer works today, their work effectively is looking at a simulator. The simulator exists. The entire frac packing process is structured. The input parameters and the output variables are structured inside the simulator, and then the engineer takes a decision based on that. So that environment exists, and that's a key requirement for reinforcement learning, especially if you're doing model-free type of reinforcement learning. So that was there. The ways of working did not change for the engineer, and that was like the one of the biggest reasons why this worked. The other area where we had to, this took about 2 to 3 months, but basically what we had to define was we had to continue to recalibrate the reward mechanism. How do you define how to penalize the agent or not? So after every time step of the pressure curve, we had to come up with a root mean square error was effectively what we chose on, and that factor effect was something that we had to choose to understand that if it goes beyond these parameters, then you penalize the agent and tell that it's doing something wrong. And if it's within that particular parameter, then you give a thumbs up. And then it keeps learning in that iterative loop, in this loop over a period of time, and eventually goes from not knowing what to do, just like the robot example that I gave, to matching human performance. And in the words of the frac packing engineer, Karthik, he says that he enjoys even looking at. So now the agent has become so good that it even predicts where the curve is going to be at 5 minutes earlier. And he says he enjoys looking, and he's like shows the junior engineers, see, it's going to go there, and it actually ends up going there. So they are building confidence in the system and trust in the system. And that's why eventually he thinks, this is not going to be anytime soon, but I think eventually, probably in a 5-year time frame, he would just be able to step back and observe what the agent is doing and not interfere. So the typical project phases for an activity in reinforcement learning is you start with the brain design. So the terminology that Bonsai uses for the agent is a brain. So you start with the design factors that I described, where you design the reward mechanism, you design the environment that you're going to train the agent in, and then you start the training. So training is effectively compute intensive, and depending on the environment and the complexity of the environment, this could take anything from days to weeks. In our case, it was a few weeks, and you do this over an iterative period. You go back to the brain design, you tweak the reward mechanism, and you keep doing this in a loop. And finally, there's the in this process, you prove success first inside a simulator. You can imagine this is a safety critical environment, so you prove success in a simulator, and only when you are very confident of the results, then you deploy it in a real world environment. And even that deployment has the human in the loop. So if the decision is still rests with the completions engineer in that context. So I want to focus a little bit on the lessons learned, but where we are going with this is currently live in Gulf of Mexico, but we see applications in other regions as well as applications beyond traditional well completions into things like carbon capture storage and geothermal, where similar skills are applied. So I think I touched a little bit on the results. In terms of our vision for this specific use case, we want to take it from its current state, where it is suggesting the results to the completions engineer, and the completions engineer is then either overriding it or going with its results. We're going to keep tracking it, retrain the brain every 3 months, develop trust in the system with the completions engineers, and eventually get to a point where it's going to be like a real-time decision-making scenario, where the way we will develop this is the simulator effectively will be able to take decisions directly regarding well completions, and there will be a way for the completions engineer to intervene if they wish to do so. And you can imagine the next step after that is to take the human out of the loop, which we may not necessarily want to do, depending on how the results progress. But at least we do know that there is a lot of demand for these skills in other lower carbon areas where these skills could be transitioned, where effectively the same skills could be deployed from a human standpoint first, and then eventually technology could take over. So what were some of the lessons learned here? From a technology standpoint, this technology, the biggest challenge, so if you were to talk to someone who is a critic of reinforcement learning, the first thing they would say is, it doesn't work. And the reason why it doesn't work is because it works great inside a simulator, and there's a reason why there's success in gaming, but when it comes to real world, it just doesn't work, because the difference between what is in a simulator and real world is just never going to be the same, right? So in this use case, it's called the sim to real gap. That didn't exist because even today they use the simulator while making that decision. So that didn't exist, and there are some other use cases where that gap is really small. So the sim to real gap is something that you should evaluate before going into any project with model-free RL. I think from a people standpoint, we hit gold on this project because the subject matter expert completely embraced it. You can imagine going into this conversation with someone where you say that this technology might eventually make some of the things that you do redundant, and you'd be sort of focusing on other more interesting areas, and people would have different reactions to this. But in this instance, the SME championed it and is going across the company telling people that this is the way of the future, we should embrace it, and we should deploy our skills somewhere else. So that was key, otherwise this project would have never taken off. And the data scientist in this instance, Andrea, she comes from a reservoir optimization and a drilling background. So if you are looking for a data scientist, you're looking for perfect data scientist, you're looking for 3 skills. You're looking for someone who has computer science skills, statistics skills, and the subject matter expertise. This person didn't have the stats, but had 2. That's pretty good. And I think that was a big reason why we succeeded in this case as well. So this is where I think Prabhu would be able to talk about as well. But we had a mix of, our squad was a mix of internal and external resources. So we had BP staff who were the SMEs and the data scientists. We had the AI engineers from Bonsai who brought in the reinforcement learning skills and the tooling knowledge associated with it. And then we had Wood, who represented both the development, the architecture, and the scaling side of things, as well as all the breadth of the subject matter expertise in this area that Wood have. So we really had got together a squad of 3 different companies, but worked as one team in one squad. And then that was effectively the team that worked in an agile fashion to take it forward. So that balance was key. We wouldn't have been able to do this by ourselves. And lastly, I think the success is the proof is in the pudding. So this is not done yet. We want to reap more benefits out of it, and the continuous training of the agent is crucial. And we are doing this for the first time as well from in the reinforcement learning perspective. So currently we have said every 3 months we will look at the data that has been generated, and we will retrain the brain. We are currently on our 53rd iteration of the brain, which is pretty good going, and we are still very confident of the results that are being produced. It is going in the positive direction that we want it to. So from that context, it has been successful. I would say, though, this is the second project that we tried with reinforcement learning. The first one was considered, although successful, a little bit risky, so it's still on the project backlog. So as things are in innovation, not everything works, but this one did, and we've learned lessons from it. And I'm very happy to take questions in the panel on this use case and others. Thank you.
So I want to ask everybody, all the panelists and the speakers, to come up, and then I'll ask the panelists to introduce themselves, and then we'll get in. We got almost 35 minutes or so to. Plus, my session's in here next, so if we go over, it's on me. So hopefully the people my next session won't be too throwing arrows at me. But so it's really, I mean, that's really impressive, Manish. That was really some fantastic stuff. I mean, I was like going. First thing I said was, "It's scary." I mean, I was like, because I know Stephen Hawking and a few other smarter people than me had said that, if we're not careful about AI, we gotta be careful what you wish for sometimes, because it. You think about HAL 9000, and you can think about all the interesting things. But so what I'd like to do is, I guess I'll just start in this order. I'll ask Varsha from Microsoft to just introduce herself real quick, and then we'll just go from there.
Hello. Hi, everybody. I'm Varsha Raju with Microsoft. I'm part of Microsoft's AI group. And the product that we have, the platform that we have, is called Microsoft Bonsai, which is what Manish was talking about. I am a chemical engineer by background. Most of our team are actually engineers, controls engineers, process engineers, chemies, even a mechanical engineer or two in our Microsoft Bonsai team. So it is an AI technology, but fundamentally it is really about serving specific control and optimization enablement using that technology. And so we have a lot of process engineers and engineers with a capital E in our team, based in San Francisco.
Thank you very much. Prabhu?
Hi, Prabhu Parthasarathy. I'm the VP of Intelligent Operations at Wood. We've been deploying real-time systems. So Bonsai is exciting because we do simulation, real-time systems, a perfect blend of the two. My background is I got a PhD in mechanical engineering, fluid dynamics, thermodynamics, but I'm an honorary chemical engineer because my dad's a chemical engineer, and I've been doing chemical engineering for 20 years. So,
Lisa?
So I'm Lisa Williams from OLI Systems. I've been there for about a year now. I'm, I think, in that one outlier here. So my background is computer information science, and I'm helping OLI come from the R&D and simulation only area to bringing the simulations out into the operations side. So we've developed the cloud API, and we're breaking those data silos and making those new results available to everybody. And as you've seen from Nicole's presentation, it's got a big impact. So it's a 50-year company that is really getting a larger amount of exposure, because we've always been in the background helping on the thermodynamic simulation. First principles, no training here. It's all science. So, and bringing that out to the operations. So good to be here and see everybody today.
And Sandeep?
Hi, everyone. My name is Sandeep Chandran with Connected Industrials Honeywell. Been with Honeywell 20 years. I'm a chemical engineer by training. At Connected Industrials, we focused on software solutions that enable autonomous, semi-autonomous operations. So there are 4 major pillars there. One is plant-wide optimization, which is the next generation of advanced process control. We're focused on asset performance monitoring. We're focused on remote operations, de-manning platforms, de-manning facilities, and finally, sustainable operations, monitoring flares, energy-intensive process operations, fugitive emissions, and so on. Happy to be here.
Thanks. All right, we got a pretty good audience, so I'm going to hopefully I got some questions here, but I want to give the audience an opportunity to, to ask their questions. And then we have a mic person back here, so just raise your hand, and then we'll get your questions going. Cavestro, great, thank you. I knew I could count on you for a good question. Thank you.
So I got a question for Varsha, but first a comment for Nicole. I grew up in Sydney, Montana, so I feel your pain.
My newest member lives in Sydney, Montana, and he's the reason why the API was necessary. He was my midnight call.
But Varsha, how big of a model can Bonsai train on now? Like a steady state simulation of an entire processing unit, for example? Can it be that big?
Yeah, we don't think about the constraints of the model in terms of the size, or, is it too complex, too enormous? What we really want to make sure with the model, so the short answer is yes, we can do steady state simulations, we can use dynamic simulations, we can use first principle simulations, so chemistry and physics models. We can use MATLAB, Simulink, ANSYS, so there's lots of third-party models we can use as well, VP-Link. But the key piece that we look for when we're looking at the simulation model that we build for a reinforcement learning application is, does that simulation sufficiently capture the variables that we need to consider and the actions that need to be taken as output? And that's really what we're looking for. Does it sufficiently capture those two things? And if it can, then we're good.
Yeah, just to add to that, I mean, when you're doing any simulation modeling, obviously you're trying to solve a problem, and you've got to take engineering decisions on what is important, what is not important, right? I mean, so for instance, you're doing a dynamic model. Sometimes you don't represent full pipes. You just put something that accounts for the time variable there, right? So you would have to make those judgments in terms of what is the problem you're trying to solve and how do you solve it. That needs to go in.
And feel free, any of the other panelists, if you want to interject some perspectives as a response, jump ball, so to speak.
One more follow-up, just out of curiosity. You train the models by running them, correct? Do you foresee a time where you don't have to do that?
Well, I think for reinforcement learning, conceptually, you'll always need some sort of model in which the agent can learn within. So as a fundamental concept, that's how the mechanism works.
Right, but it's totally predictable what the model outcome is going to be. All the rules, everything you need is described in how the model's going to be.
The PDEs. No,
Correct.
so if you look at some of the research that's going on today, and it's hugely sponsored by NVIDIA, there's a new, I worry about this because I think existing engineers cannot take that up, but something called PINNs, which is physics-infused neural networks. It's a huge area of research. It's phenomenal. They've already started representing heat equation, Berger's equation, all sorts of equations with pins. So what they're doing is neural nets already infused with the results of the PDEs that you're trying to solve. It's going to revolutionize, in my opinion, how you build simulation models. So it's going to be 5 to 10 years from now, but it's going to happen.
The other area in research is something called as imitation learning, which is relevant to what you said, where the training happens by watching an expert's actions. So where simulators don't exist, the researchers are thinking, what do we do then? And that's where some of the research I've looked at is to sort of Berkeley doing some research in training a robot to fold laundry. And they are looking at one type of clothing, one way of folding, and there's a video of that, which the agent is learning by watching the video. That's called imitation learning, because a simulator of something like that doesn't exist.
And to be clear, when we use the word simulation, it doesn't have to be a complex, dynamic simulation or first principle sim. I would say for most of our projects that we do, the simulation is what we call a data-driven sim. We take DCS tags, we take Excel spreadsheets, and we build a data model, and that is the simulation. So it doesn't have to be particularly fancy. And the other nice thing about reinforcement learning is you don't need it to be super complex and super specified. You need it to be sufficient, but unlike some very hungry supervised learning models or other machine learning models, where you need maybe a very high data source and data fidelity, even for those of you who are controls engineers, APC engineers, who are comfortable and familiar with model predictive control, you'll know that the underlying models in MPCs need to be of pretty good fidelity for them to be making good control actions and really optimizing that process. You actually don't need that level of fidelity in reinforcement learning models, simulation models. So you've got a degree of flexibility there.
Got another question up here? Yep.
Yeah, Varsha, I think that point made me wonder more about, I want to understand reinforced learning a little bit more here. I guess in my mind right now, it seems to be this way of taking AI, pure black box, to hybrid that with more first principles. And we mentioned multivariable control just now. I did run into this example of Microsoft Bonsai. Someone was doing this balancing the broom exercise.
Yeah, cart pull.
And then when I saw that, I said, wait a minute, I look at this equation. This is basically quadratic dynamic matrix control, and so I was wondering, like, is reinforced learning, applying, I take an equation like that, which is basis my experience as an advanced process control engineer, or can I apply even things like first principle, things like thermodynamics?
Absolutely, yeah.
Reaction kinetics, and so on. So this is kind of this hybrid of AI and black box AI and my first principles knowledge. Does that sound right?
Yeah, so a lot of the demonstration you're referring to is called cart pull, and it does capture that motion, that movement in a quadratic form. But to your point, the simulation environment in which an agent, a reinforcement agent learning can train, can include equations, explicit equations that you may have, but it can also use thermodynamic models. We use computational fluid dynamic models. We can use literally linear equations that may be relevant for that particular part of the process. So we use a combination of those things as needed in order to represent the process that we're trying to optimize.
So I would say, think of it this way, right? So you're basically running millions of simulations and building a multi-parameter correlation. I know she gets angry when I say that, but as an engineer, that's how I look at it, right? So you're running this huge set of simulations. Each parameter, how does it impact the process? In your learning, it could be just steady state or it could be dynamic, but you're essentially learning how does each parameter impact the parameter you're trying to control, building this memory of that and using that in real time. So you moved all the computation from the edge to the cloud a priori, and at the edge, you're just doing a quick search scan through what memory you've built and finding the solution quickly.
So I guess my real question is then, what's the advantage that you see, from traditional APC approach or traditional optimization approach, if you will, with some...
Excellent question. So a couple of very specific advantages you get with deep reinforcement learning. One is that where your MPC or APC systems or even PID systems are not sufficiently controlling and optimizing your process because of a much more highly dynamic system than you've modeled in your existing MPCs, APCs, that's an area to consider reinforcement learning, a very highly dynamic process. So feedstock composition is changing. So if you're in oil and gas, refining, for example, you've got changes in crude slates, you've got changes in crude baskets, maybe you've got a chemicals process where feedstock composition changes over time because of various reasons. That's one that's difficult for typical MPCs, APCs to constantly and consistently control well. Another example of where reinforcement learning would be extremely useful is when you've got multiple competing optimization goals. So we work with customers like Pepsi. Pepsi makes Cheetos, and when they make Cheetos, they use extruders, and they've got trade-offs to make. They've got decisions around how do I maximize yield on this Cheetos process, but how do I make the best Cheeto quality I can? So when you've got a process that has to make real-time trade-offs and short-term trade-offs in service of long-term payoffs and decisions, that's again where reinforcement learning can work really well versus MPC, APC. The other piece, I would say another superpower of DRL is related to sensory input. So unlike APCs, vision systems, vision input, auditory input can be considered by reinforcement learning algorithms. So when an operator says, when we're working with mining companies, I listen for certain sounds on this equipment, and that's how I know to throttle this setting or set point up or down, or I have to override my MPC or APC under certain conditions, because it just doesn't work well when I've got slugging or when I've got sort of water entrenchment or I'm hearing a certain sound. Those kind of strategies that your SMEs, your operators, your technicians use today can be incorporated into a reinforcement learning agent very elegantly in a way that you can't with APC, MPC. And the other final piece there is what we call unknown states. And this is where, again, with APC, MPC, you have to be able to explicitly quantify what is happening in my process and explicitly delineate the variable, like moisture. I want you to track moisture as a variable. I want to track, concentrations. With reinforcement learning, you don't need to be explicit about all of those variables. It can learn. That's what Manish was talking about. It learns through trial and error. What are the factors that are important on top of what you've already specified, and can create those correlations when it's trained. So big point I'd want to say is we're not saying you replace PID or MPC or APC with reinforcement learning. That's not the takeaway I want you guys to have. It's about saying where you have those technologies, great, and if they're working great, awesome. Where it's not working well, or where you have further opportunities to optimize your process, that's where you can take a look at reinforcement learning to complement those existing technologies.
It's a more of a layered approach to analytics. So, for those of you that had the unknown checked at the beginning, you can start at those lower levels. But no, it's not going to be a throwaway. It'll be able to be incorporated into these newer technologies that are coming online. So make sure you think about that. There's less technical debt today because we're not starting from scratch. We're incorporating all of these things that we're doing, even at the first principle level, where I'm at, up into the AI. I think that's important for everybody to understand as you go through your investments and trying to make sure that you're, getting the right justifications.
Great point. Any other questions to the audience? Raise your hand. You won't be shy. Okay, well,
You had a quick question for Oli and Lisa or Nicole. Nicole, outstanding presentation. Enjoy listening to that. Definitely some unique challenges in your area. But particularly the cloud aspect of it, with your application being cloud-based, it sounded like one of the core challenges for the region was communications. How are you supporting the cloud connectivity in that environment then? I didn't hear how that piece was being addressed. I heard what you're doing with it, but how do you address the connectivity piece?
Did you want to answer that?
Yeah, I can answer that. Luckily, our offices at least all have pretty decent connectivity. So specifically with the cloud that we utilize, our database currently is housed specifically only on our server within our building, just due to security purposes. So as long as somebody is within our facility, then we're able to run the cloud and we're able to connect up through. So it is required that it does actually always have at least some sort of internet connectivity. So as of right now, for us, because we are a very limited staff, we do only run the software whenever somebody is actually within the building that has both access to our database along with the internet connection to be able to get to the cloud and retrieve the results back in that time frame. So from there, once it actually is able to be pushed to Azure, then we're able to use just like a standard web browser. So if somebody theoretically, though, did not have connection to a web browser at that point due to being in the middle of nowhere, at that point, we wouldn't be able to fully utilize the results. So for the most part, as long as there's cell phone reception, everyone's able to work pretty well. But in our remote areas, normally, luckily our engineers have not needed that access, but if they do in that instance, as long as they can make a phone call, then they work with one of us instead. But that's kind of our main point to it is we are still very much restricted to somebody has to be within the office to be able to utilize that due to the restrictions of our area.
Can I have another question on what you talked about? I've done scale analysis myself, so I know how, the data can be, the measured data could be different conditions. You got to check all of these. So there's a lot of quality control of the results that need to be done. At the scale that you're looking at, 3,800 samples to be tested, what is your quality control process when you automate the results generation, but how do you then vet the results that come out and say, okay, I've quality controlled it, that I can use it? What do you do there?
So from the original quality control standpoint specifically was testing the original studio that was developed by OLI versus the cloud. From any point past that, it's mostly in our lab to have a certain quality control standpoint. All of the results that we do push through this software are originally from our lab in Williston, so they have to meet the lab's quality standpoints. So it's pretty standard for like in clear analysis, like a 10% cation anion balance. As long as they meet that point, it will go through. If there's any specialty ones we're looking at and there happens to be something flagged or interesting, then we'll look into it. But for the most part, we've done a couple different runs, even further through to check the original API versus not only field results, but also the original studio, and everything's matched up for the most part for us. It's a very on-point software, which is not amazing because it keeps telling us that we have problems, but other than that, it's a good time.
Great. I had one more follow-up question also. Manisha, as you're talking through the application here and the future plans for those things, lessons learned, any tips or thoughts on how to further accelerate the learning process or the deployment process for future applications or in other applications they run across that would help get the value to the field faster?
I think the lesson that we learned from our two lessons that we learned from our first use case, this is the second use case, were the simulation was the first, where as Varsha mentioned, the simulator doesn't have to be like a full-fledged reflection of the real environment. And we started, and that works for some use cases. So in the first use case, we started with a Python script model that was our simulator. But the environment was so dynamic that it wasn't well represented in that script. So we had to pause and we had to change to and sort of get licenses to a third-party simulator effectively that did a much better job of that. So in some use cases, it works if it's just a model, but in some other use cases, it doesn't. So that was like a lesson we learned to understand what type of use cases require a proper simulator and what doesn't. So that was one. And second was, in our first use case, we did not have the data scientist with the appropriate subject matter expertise as well. So I think that's a combination we definitely deliberately wanted to wait for and find the right candidate for. So those are, I think, the two probably the sort of make or break type biggest lessons from that perspective.
Anybody else doesn't have any questions? I want to ask Sandeep a quick question because I was really intrigued by Raid's presentation. And we're looking at that project, Sandeep. Could you just sort of elaborate on what was the justification of the project, and then how did you and Halliburton measure the ROI?
Well, for this particular use case, there was not a lot of justification required. It was essentially translating a manual workflow into a digital workflow. And as it exists today, because of the manual workflow, as Rad explained, the actions are reactive. The data comes in maybe 2 days after the fact, and there's not much you can do with it. So with this, it was more about getting data as close to the events as you can, fixing problems as early as you can. But the big picture here was the integrated workflow from the well to the surface, which needs certain data points, and getting this data in enables that workflow. The side effects of this are justification from a safety point of view. Now you have the what we call the deskless workflows, workers connected, so you can pass on information to them to make ad hoc site asset visits, keep them safe from emissions, environmental or other risks that might happen on the field. So part of it was to bring these remote workforce into the mainstream digital ecosystem that we have. But the big picture is to build some digital twins, build some models that connect the wells to the surface and have all the data available to do that.
Okay, Lisa, Nicole talked a little bit about the OLL cloud, excuse me. And I wanted you to see if you could elaborate that in terms of, what about some of the performance characteristics, scalability, easy use, things like that. If you could elaborate a little bit to help us out to understand.
Sure. So we've taken our classic desktop software and broke them down into individual RESTful APIs as endpoints. So we've got, the engine, which is more of a stream analyzer, corrosion analyzer. So we do scaling and corrosion, ScaleChem, and even our process API. So we've taken our flowsheet ESP and turned that into something that can be run continuously. And just looking at the statistics that come across from our customers, we're seeing, even on the small install, which is, capacity, how many calcs you're running at a single given time, they're running 30,000 calcs at a time in a day, and they're not hitting those limits. It's just a continuous pattern that's happening. So, I feel fairly confident in the things that we've been doing and seeing on our scaling to be able to go up and make that even more. So being able to help learn and feed into those other AIs is very, very interesting to think about with the scale of the cloud APIs. I think the other piece that I get really excited about is thinking about you've got how many years worth of history. So I spent 20 years in nuclear, and I put in a historian in 1999. So I know there's 22 years of data there. I can actually go and reprocess all of that and tell you how much has your, a piece of equipment been exposed to a corrosive environment, or how much scaling has been building up in that piece of equipment, maybe since your last turnaround. So it's not necessarily learning, it's a couple of days to go and run all that data and bring it in and start to be able to make the insights and bring what's the condition of the plant to a more complete picture. So, yeah.
All right, I'll throw it back out to the audience. If anybody's got a question, raise your hand. There's some really great discussion here. Got one right there. If you could just tell us who you are, where you're from. I've said that earlier, but it's...
Yeah, Andrew Vanderpool, Phoenix Contact. I have a question for Manish. So because machine learning is probabilistic at its core, and you are using it in a kind of safety application, what is the crossover point for when you can trust it? Because even well-trained models can do really weird, unpredictable things that shouldn't have happened.
Yes. So I think the analogy that comes to mind is, so in the, to that point about like weird, unpredictable things, in the, when the competition I mentioned earlier, AlphaGo, which is this ancient Chinese game where it was playing against the world champion, this is like every move is documented and studied by the geeks of the game. And there was this one particular move in game 2 where the commentators, and the first game the computer had lost, and this particular move, the commentators were like, this agent is just stupid. This has never been done before. Ended up winning that game, and that sort of that move is now revered as like, oh wow, this is creative, genius, this computer. So I think in a completely unconstrained environment, sometimes those crazy things might work as well, but in a safety critical environment, you define the envelope of it. So you don't let it go that crazy, right? So you just define the safety envelope, and that's your environment to play in. You can test the boundaries inside a simulator, but in deploying, you always, what I've learned from the SME is that you define that safety envelope and that's it, and we won't go beyond that. And in terms of then operationalizing and the deployment of something like that and gaining trust, we don't know like when we are going to do a full handover and how that trust is going to be established. But I think the current intuition is that we would let the current way of working, where the agent is suggesting to the human and human eventually takes the decision over a period of couple of years at least, establish the points of decisions that have been made, and then take a percentage calculation of how accurate they were over a period of time, and then perhaps put some number around it to base autonomy on. But right now, don't know whether we're going to actually be fully autonomous or not.
I'm going to interject.
Yeah.
So I would add a couple of other things to it, right? So one is, even from the field data, when you're making decisions, there are always going to be anomalies, right? So if you're looking at closed loop control, you do have SIS systems, you have your existing control systems that do put a barrier against those kind of decisions, number one. Number two, when you're looking at SMEs making decisions, you are relying on some of their intuition, subjectivity, when they're looking at data that's outside the bounds of what you've seen. And that intuition can be baked in, but it's part of the design process of the brain. Yes, you may not be able to get everything out of an SME sometimes because it's just intuition. Like when I did some of my PhD simulation work, there were things I could see that I can't explain, but when I see a pattern, I would stop my simulation because I knew it was going to blow up. I would just look at how the data moved on the screen, and I knew it was going to crash. That's intuition, but you will have to dig into that intuition, get it out of the SME as part of the process as you get more fidelity. But you do rely on your base SIS and control system as well here to provide the guardrails. So, so it's not just it's going to go berserk and take over the world like Skynet did. But maybe someday, if we completely rely on it, maybe it will, right?
Just a small question. Do you think that we are going to have like a toolbox for AA that any chemical engineer can use without calling a data scientist?
That was not a planted question.
Holy cow, that's like in our tagline. Yeah, so the Microsoft Bonsai platform it's low code, and it's meant for chemical engineers, mechanical engineers, controls engineers, production schedulers. We have a lot of supply chain and logistics use cases you can use reinforcement learning in. So it's meant for people that are not data scientists, because we recognize that the data science population is growing, but it's a very small percentage of folks who have deep operations and SME knowledge, and folks that really understand the kind of controls and process aspects of the business that they're trying to optimize. So the platform is actually intended for exactly the audience you described. So you don't need to be a data scientist. It's low code. It uses a visual kind of interface as well. So, a gentleman there asked about black box. One of the things that we really want to try to create there in the platform is transparency. So it's not so much of a black box. MPC can be a black box, but a lot of our teams and engineers and technicians have gotten used to it. We're trying to create transparency with the platform, with the visual aspects of it, so that you've got better insight to why the agent is recommending or making the decisions it's making, so that when it is in full control, closed loop control, you've got more understanding around decision making, and you've got engineers actually input into design.
Okay, I just wanted to interject. I had one question that I wanted to ask Sandeep again that I brain dead here. You talked about where we are with the sort of workflow digitization. What's next? What's coming beyond that area?
Right. I guess if you guys recall Riyad's last slide, which was a subsurface to surface workflow. Now that's the end goal. That's the nirvana of the oil and gas world. Just because the organizational challenges today with most IOCs, you have an upstream organization, a downstream organization with their own objectives, KPIs, own systems. So there is a reservoir system, a well system, and then there are the surface systems. There's absolutely no availability of data across systems. So one of the end goals from this program is working with Halliburton is pulling all the data, the subsurface systems, surface systems into one place where you can run twins. So we have in Honeywell surface digital twins. Halliburton has got the subsurface reservoir models. So how do we run these models end to end to replicate what's happening on the ground? So that's the end state. But all that requires data. So we're starting with the basics. Let's get standard data in. Once we have the data in, the models are a bit more accurate. Users trust the model with the outcomes and advisories. And it's a step towards integrating the workflows across upstream.
All right, since I'm moderating the next session, I'm making a command decision. We're going to take a few more seconds. I want to ask Lisa any final takeaways you want to, and then Prabhu and Varsha. Any final takeaways from that?
I was just going to add on to your end piece there, that trust. I mean, it's huge when our people don't trust what we're giving them as software vendors, providers, solution providers, and being able to say, yeah, I believe in it. And that's one of the things that's core for me. I love all this technology stuff, but if I can't walk the plant floor and help people understand how it's going to benefit them every day, then it's for naught. So that's something that's very near and dear to me. So I like the people aspect of it there. So it would be my final thought is don't forget the little guys out there.
Yeah, so one last thing, there was a question about SMEs, right? How, can engineers build AI? For me, I give an example, and Jack makes fun of me. I built an AI agent myself in about 3 days. Small problem, but I tried it, and I was able to do it. So it was an interesting thing for me. So, but there is a big gap in upskilling, So we talked about 10,000 data scientists, maybe 100,000 SMEs out there. How do you scale this is going to be the next challenge. So we're working with Microsoft to do that, Center of Excellences, working with clients. But to me, that's an exciting phase because we really want to be able to empower engineers to build this on their own. Because once they build, the question of trust. If they build it, they trust it. Mm-hmm. If you build it, there's going to be a lot of questions, But we want to empower, engineers to do it and scale it because if you don't scale it, then, so that's the key.
Rasha, any final thoughts?
I want to just mention again where this all starts. It's with Manish's first slide, which is around value. We don't usually try to say, hey, we've got a technology, let's see where we can stuff it in your system. We really want to start with what are your optimization goals? What are your control goals? What do you actually want to improve? Is it yield? Is it throughput? Is it quality specs? And you got to start with that kind of guiding light and be really clear on what are the goals you need, what are the KPIs that are associated with those goals, and then you figure out where the technology can support and enable that. It sounds really obvious, but sometimes we can get excited with the shiny new toy. And I know we are a shiny new toy, but we always try to recenter and start with first principles, which is what's your goals and is it of value?
Great. Well, I can't thank you folks for sticking around a few minutes later. I can't thank Manish and Nicole and Raid and the rest of the panelists. It's been for me, it's been fantastic. And I'm still a little bit nervous about some of this this advanced learning stuff, but that's all right. I'll get over it one of these days. Hopefully by then I'll be dead. Don't have to worry about it. But anyways, because I always wonder where's mankind going to be in 50 years from now? And
Tim, Skynet will send Terminator back to kill you.
Yeah, I know. Yeah, that's right. I'll be time traveling by then, right? Anyways, I want to thank you very much. If you're interested in drones and things like that, I have a session here at 10:30, so feel free to stick around. If you're traveling back today, I hope you have safe travels. And thanks for everyone very much for coming to the ARC Forum, and I hope you get a lot of value out of this session. And again, thanks for speaking.